Okay, we're going to start our next Laplace transform problem. And so let's see what we have here. I have a third order differential equation, third derivative. Uh, so it goes to plus 6y double dot, 11y dot plus 6y equals. And here I actually have a derivative of the input, perfectly valid. This would be a pain in the butt if we were dealing with uh, method of undetermined coefficients, but for Laplace, it's a no-brainer. It's really straight. It's just it's a little more math we have to deal with, but it's very straightforward. Okay, here we have y of 0, initial condition is 1, but y dot of 0, y double dot of 0 are both 0. So we got three initial conditions because we're third order. X of t is again a step input, and because I got a derivative, I need its initial condition, so the input starts from 0. So that's okay. All right. So that what we need to do now is we need to get the Laplace transform of the differential equation. So we do what we did last time. Okay, but before we start that, let's do a little analysis. Okay, we can check out the static gain. If you let all the derivatives go to 0, so 0, 0, 0, that's a derivative, so let that 0. We have 6y equals 6x. Divide through the 6, we get y equals x. So static gain is 1. So that tells us that if we were to look at this problem, we check out the steady state value. If you have a unit step input, the static gain is the gain on that. Well, that's a factor of 1. So it says the final output should be a 1. If you have a unit input which starts at 1, it'll end at 1. All right. Okay, if you were to get the roots here, so based on having lambda cubed plus 6 lambda squared plus 11 lambda plus 6 lambda equals, or plus 6 equals 0, there'd be no lambda there, get the roots of that. Well, you can do that quickly on MATLAB or a lot of calculators. You'll get s equals -1, -2, and -3. So we have 3 poles, eigenvalues, roots, whichever you want to call it. All right. And so this is the one closest to the imaginary axis. So this is the dominant one. So the system time constant will be 1 second. And 4 seconds gives us our system settling time. So this will take 4 seconds to settle. These two will settle faster. All right. So we've done our analysis of stuff we're expecting to happen. And now we're going to introduce another thing called the Laplace final value theorem, which we'll use here in a moment. And so that says the final value of a Laplace transform represents some dynamic thing. Okay, we had a 1 over s represented as step input. All right. So when we form y of s out of this thing at steady state, so as time goes to infinity, we can figure out what that is. It's the limit as s goes to 0 of sy of s. Now, this is the reason why for this limit to exist, it must be possible. The Laplace transform must be valid for all s. So let me put this in other terms. So we have our imaginary axis. Here's real. Here's imaginary. And when we did the Laplace transforms, we had one where we said as long as the real part was greater than 0. Bottom line is if your Laplace, to use this function, the Laplace transform must be valid so you can have a line of sight. This limit as s goes to 0. That's right here. So before what we had, we said it was valid for everything greater than 0. Laplace transforms, when you go through the motions, there's going to be some point where you can draw a line, and everywhere to the right, the limit exists. So here's the exist side. Here's the not exist side. To be able to use this property right here, you need to be able to find one path from infinity that can go to 0. So if I'm out here at quote unquote infinity, I can go into 0 and I can take that limit and it's valid. If I start from over here, I hit this wall and I'm done. okay? Because this limit doesn't exist anywhere out here. This doesn't work. I need to find some place where I can go from infinity, and infinity is all around here, okay, and have a straight line into the origin and have the Laplace transform be valid. So where does the limit exist? When do you care about that? If you want to use this. And in most cases, here's the reality. As long as you have a stable system, that's going to work. Basically how it comes down. All right. So this isn't really terribly important in terms of limits existing, but this is very helpful. You simply get your y of s, multiply by s, let s go to 0, and you can find the final value. Okay. So let's Laplace transform this thing. We'll flip this over. So I have to Laplace transform y triple dot, s cubed y of s, and then I just drop down powers of s squared y of 0, minus s y dot of 0, minus y double dot of 0. These are both zeros, so we can ignore them. Then I have 6 times s squared y of s minus s y of 0, then y dot of 0 is nothing. We have an 11, sy of s minus y of 0. Y of t simply becomes y of s. All right, and this didn't show up here. So now I have x dot, that becomes x of s minus x of 0. That's why we needed that initial condition, plus 6x of s. All right, once again, we're going to gather terms for x of s and gather terms for y of s. So we have s cubed plus 6s squared plus 11s plus 6s, that's right here. And on the x terms, we have an sx of s and a 6x of s. So it's s plus 6 times x of s. Then I take all my initial conditions, blast them to the other side, and substitute in y is 0 equals 1. So I have s squared plus 6s plus 11 times y of 0, which is just a 1. All right? When I've done that, I take this characteristic polynomial, divide it through. So let's see what we have. This term is the transfer function times the input. Transfer function, input. This is based on all the initial conditions. This is the initial condition response. And we have a step input, so we know x of s equals x of s, 1 over s. And that goes in there. So we will naturally create our forced response and our initial condition response. And we'll find that that would go to 0, and that's a mark of stability, as we learned. All right. Final value theorem. All right. So we're applying our input, 1 over s, times here's our transfer function. Okay, so it says multiply y of s, and this will be for the forced response, times s. There that is. These will then cancel. Take the limit as s goes to 0. 0, 0, 0, 0, 6 on 6 equals 1. And that makes sense because we had a unit step input times static gain is the output. So 1 times 1 is 1. Final value is 1. Everything works. All right. Next step we want to do is we want to take all this and go back in time and see what we got. So let's make that happen. So here's our forced response in terms of Laplace. And so what are all the roots? S at 0, and then this had roots at -1, -2, and -3. So that'll all expand into a over s plus b over s plus 1, and I'll say c over s plus 2, and d over s plus 3. So now we're going to use that residue theorem, and we're going to compute all these things. So a, if you look at this is the root at 0, so I'll take the limit as s goes to 0, multiply this side through by this s, cancel the s's, let s go to 0. We have 6 over 6 equals 1. All done. The b, I multiply through by s plus 1 on the other side. That's what I have here. And I take the limit as I go to what this root is, s equals -1. All right, cancel that out. For every s, put in a -1, you get -2.5. For c, roots at -2. Multiply by s plus 2 on the other side. Take the limit as s goes to the root, minus 2. So everywhere you see an s, put in a minus 2, works out to 2. Likewise for d, multiply through by s plus 3. Take the limit as s goes to minus 3, what that root is. Cancel these out. Everywhere else you see an s, put in a minus 3. And I see I forgot to put the line in here. Get a minus a half. All right? Well, once we've done that, I have a is 1 over s, but 1 over s is just a step input, so that's a 1. And turns out that the inverse Laplace transform of 1 over s plus a is e to the minus t times b. So there's a minus 2.5. 1 over s plus 1 would be e to the minus t. S plus 2 becomes e to the minus 2t. S plus 3 becomes e to the minus 3t. And there's our forced response. Okay. And so let's, and if you check this out, here's something interesting. If you look at time equal to 0, you'd have 1 times 0. This becomes minus 2.5 plus 2 minus a half equals 0. The forced response always starts from 0. And so we have that worked out. All right, now we have, this was the initial condition response. There's 3 roots, s plus 1, s plus 2, s plus 3. I will leave you to take a look at these numbers. You can stop and check everything out, but we're again just doing the residue. In this case, multiply s plus 1, s plus 2, s plus 3. We take the limits to the appropriate points. I'll leave you to check this out. You should have done this in math previously. But you take the limit, you wind up with b is 3, c is minus 3, hard to see. And here we have d is 1. All right. And again, anytime the Laplace transform, I'll just put this in here, of e to the minus at equals 1 on s plus a. So this shows up a lot. So you fit this model to these, and you get 3e to the minus t, minus 3e to the minus 2t, and then you have a plus e to the minus 3t. Now, curiously, what happens if you let t be 0? Okay, you get 3 minus 3 plus 1. Here's our initial condition. And if you want, you can take derivatives, and you'll find out y dot of 0 equals y double dot of 0 equals 0. All right. So once you've done that, we'll note you can take your forced response that we found, and here is your initial condition response. And if you want, you can just add them all together, which we've done here. And here's the total response, just all added up. And that's all for this problem. We'll do one more.